We're Rod and Tarek, and we're here to say we love Mars in a major way. We need Mars samples to understand, but its multi-billion budget has gotten out of hand. We've got Rob Manning here to explain why Mars sample return is such a pain.
Podcasts you love.
From people you trust.
This is Twit.
This is This Week in Space, episode number 112, recorded on May 24th, 2024. Mars on pause? Hello and welcome to another episode of This Week in Space, the Mars on Pause edition. I'm Rod Pyle, editor-in-chief of Ad Astra Magazine, and I'm here, as always, with Tarek Malik, the impulsive editor-in-chief of Space.com. How are you, my friend?
I'm doing well, Rod. I'm doing well. Wearing red for Mars, right? I got my Curiosity shirt on.
Well, I'd look at this.
Oh.
When's the last time you saw one of those?
Oh, nice.
Yeah. I saved it just for this event. The other one has holes burned in it. And of course, appropriately, we're joined by Rob Manning, the Chief Engineer Emeritus, just recently, of Jet Propulsion Laboratory. Thank you for joining us, Rob. I feel like I saw you just yesterday.
It feels like just yesterday, doesn't it?
And we did see him just yesterday. It's
it's great to see you. It's great to see you too, Malik. It's this my Tarek, my work at JPL has been very busy over the last few years, but now that I've transitioned away from being chief engineer, I can breathe again.
So the reason I mentioned it seemed like I saw Rob yesterday is because I did see Rob yesterday because I'm at the International Space Development Conference out in West Los Angeles near the airport. And Rob was kind enough to come down and speak to about 500 very enthusiastic kids. And then also at the luncheon, we had another large crowd where we talked about his career, which is something I've envied for a long time. So it's fun to hear the details. Before we start, however, I want to remind everybody, as I always do, to do two things. One, be sure to like, subscribe, and all that stuff to our podcast. And two, be sure to send us your best works or most indifferent space joke. And you'll know why in a second, because, hey, Tarek.
Yes, Rod.
This is from Larry DuPont, by the way. Thank you, Larry. Hey, Tarek, NASA is launching a satellite to say I'm sorry to the aliens. They're calling it the apology.
Oh, I get it. It's a word pun.
Thank you for pointing that out.
Good.
Yeah, I know. It's always painful. All right, so let's move away from that. Enough of that stuff, because I have another joke. And
you have two.
It's called Starliner.
Oh no!
So of course, there's been a lot of conversation here at the conference about Starliner and the delays, and we just had the BBC asking for interviews last night about, hey, what's up with Starliner? And it's like, what do you say?
Well, Starliner's not up.
What do you
right? say?
Yeah.
What's up with Starliner is that Starliner is not up. In fact, just before we started recording this episode, NASA had another press release. Had a much asked for press conference where they finally kind of dished about what's going on. When you and I last spoke, we were lamenting the latest delay with Boeing Starliner, and it was slated to launch on May 21st. They then delayed it again to May 25th. They then delayed it again to June 1st, no earlier than because of some challenges with this helium leak on the service module of the Starliner spacecraft itself. What we did hear from today, the folks like Steve Stitch and over at Boeing too, is that while they were researching this helium leak, they did find that there was potential concerns for the reaction control thrusters that the helium, leak is part of. The pressure, pressurizes that whole thing, that it could lead to a loss of redundancy during the reentry portion of the mission, which is not good. So they're working on resolving that. They say that they do feel that they've got the margin that they need now, that they understand what the problem is now, but that it's been a very difficult problem to figure out because it came up while they were working on the replacement for the helium valve itself. Anyway, so a lot of kind of back and forth, and there was a lot of animosity, maybe not animosity, but a lot of public calling out in the space media over the last week because of the sheer lack of information. We were just getting one-line like emails and updates saying, oh, it's delayed again, or because they need more time for this, and there wasn't anything explaining exactly what the issue was with this helium leak that they were seeing. So we finally got that today, and they apologized for the lack, but they said it was because they had their own challenges trying to understand what was going on, and they wanted to make sure they understood that before they had the press conferences or calls to explain it.
Okay. So we have an engineer here today. And Rob, I don't want to put you in a corner about SpaceX versus Boeing or anything, but a more generic question, what is it about valves that's so tricky? That seems to really be bedeviling this project.
And that's really not so much valves. It's just that so many of these pieces of equipment, and particularly for propulsion systems, they're pretty darn sensitive sometimes. Particularly, they have very tight. In order to keep the seals, especially things you're doing like helium, where single atoms can sneak out so easily.
Yeah,
seals have to be very, very tight, and even the slightest bit of contaminant materials in the fuel or oxidizer, whatever that you're flowing, can gum these things up and stop them. I'm a trumpet player, and we have these valves, right? And it takes even the tiniest little hair in the valve to just jam it all up, and it takes a fair amount of work to get it clean. So it's very difficult. It's so easy to get it wrong because of the precision required to get those seals and to open it up and close these valves elegantly and reliably. That's one issue. We've challenged us with that, and there's also a wide variety of different kind of valves. The ones in these missions tend to be reusable, which means that they've got to handle a lot of cycles, and that makes it even more challenging.
All right. Well, let's move on to a happier topic. From space.com also, we have Euclid Space Telescope returning images of cosmic light.
Yeah, that's right. So Euclid is a European Space Agency telescope, but there's scientists at JPL who are also involved in the studies too. And this is their big dark universe mission. It's designed to seek out the true mysteries of like dark energy and dark matter. And while it's taken its first images in the past, what we got this week were just brand new science images that they were really looking forward to see. They're looking at universes, galaxies that we've never really seen in such detail before. And they've called it, I'm going to quote, "It's absolutely amazing. It's just so much more than I ever expected. Euclid will be a game changer for astronomy." That's how excited these astronomers are about these images that they're getting from the space telescope itself. And they looked at amazing views of images. In fact, we have a New York Times link that is really nice for the folks on YouTube to really be able to see it too on this one. But this is a mission that launched in 2023, had its first flight shortly thereafter, and now it's getting into the science and the meat and potatoes of its mission. They call it their early release observation. So it's the first kind of big, beautiful images packed with data and science that now all of the scientists, both on the mission team and the folks that have access to the archive, can start looking into what it's telling us about dark energy, about dark matter, these unseeable, undetectable types of objects in space or of matter in space that we can only infer by its gravitational influence on the stuff around it. They think that like some 68% of the universe's energy and matter is comprised in these dark things, and that dark energy makes up about 68% of the universe's matter budget, and dark matter is the other 27%, and we get like what? About like 4% that we can see out there. And they really want to crack that nut with this mission. So these images are they're truly spectacular. And what it does suggest is that it's doing its job. Euclid is just like James Webb is working well, is offering some tantalizing morsels of what's to come over the next years and hopefully decades of the space telescope. And maybe we'll finally understand all of this unseeable hidden stuff that continues to elude us.
Rob, do you understand all this dark hidden stuff that continues to elude us?
Oh, of course, I have all the answers.
Well, that's why you're here.
No, I find the excitement in astronomy right now is through the roof, and it's all justified. We've learned so much from trying to figure out why the standard model doesn't do the job in terms of explaining the dark sectors, they're calling it, and so and it's really just, these are just fascinating mysteries, and nothing excites an astronomer or any scientist more than a big mystery. And this is so cool. I mean, we're seeing, in fact, we may be even seeing signs that dark energy may not be something that's constant. It's maybe changing even more over time. We thought it was in the 90s. We see that the universe is accelerating as the kind of the forces of expansion, they are forces, or kind of outracing the gravitational counterforce. Yet now we're seeing potential with the DESI instrument at Peak telescope. We're seeing potential signs that the dark energy is not constant and with time. And so that just, if that's true, and it's still tentative, it's blowing people's minds, because it may not be just a feature of space itself. It may be something else going on. And so this is an exciting time. Oh my God, to really understand our universe, and these mysteries are just lingering. And the fact that all experiments to see if we can find a sign of dark matter have so far not revealed very much. WIMPs seem to be wimping out. Anyons, axions are looking maybe a possibility. Who knows? It's the cool thing is that they're actually whittling it down and eliminating. The question is, what's left? It may be something we've never even possibly conceived of. So this is a great time. What an exciting time.
All right. Well, let's go from this to talking about Mars. And we will do so right after the short break. Stay with us. All right. We're moving on to Mars, one of our favorite places to go. And when we go to Mars, we think of Rob Manning, because he's been to Mars as much as anybody on our planet. So, Rob, if you could just give us a brief recap of where you've been, what you've done, and what you're embarking on now, your new adventure.
Well, many people know I've been doing this Mars stuff since my mid-career at JPL in the early 90s with Mars Pathfinder, and we helped kind of open up the door to surface exploration and helped create and open and write new chapters about what we understand about the surface of Mars, along with a huge number of wonderfully talented people from who develop science instruments and scientists from orbit, and huge teams of people from all over the world. But I have to admit, it's been just an incredible thrill to see this, to see so much about Mars being revealed over the last decades. It really does feel like I've been turning the page one after another with many other people, and helping them do that by creating these machines that they can land and explore the surface of Mars and study it more carefully. But so lately we've been. Oh, go ahead. Yeah. Go ahead, Rod.
Well, I was just going to ask if you could kind of update us on the current status of Mars. So we have the two big American rovers still exploring, Curiosity and Perseverance, a whole fleet of orbiters, and then of course some international stuff happening too.
Yes. No, yeah. We, at least in the NASA side, we have several orbiters that are doing their thing. It's it really are advancing our understanding of Mars, because Mars is an evolving place. It's not static. And as we collect more information about the surface of Mars globally, we learn a lot of things about it. We've learned, for example, that Mars is not just was a wet place and a habitable world for life 3.5 billion years ago, but Mars continues to evolve, and water plays a role in the form of ice. and there's vast stores of it underground. Great place. Anyway, Mars has turned out to be a very exciting place. So we have 2 rovers still working on Mars. Curiosity rover, it's been there since 2012, and it's been slowly walking its way up the layered terrain of Mount Sharp in Gale Crater. And it's, the cool thing about Curiosity was really within a year or so of landing, we were able to confirm that it's just that at the crater floor where we landed, there was once water. There was water, not just and not just a little bit of water, a large amount of water that had altered the clays and had that water from geochemical analysis we did on the rover convinced us that the water was fresh water, drinkable. It was ideal for a place, an environment for life to have survived and thrived if life was there 3.5 billion years ago. We couldn't see life though, because it's a long time ago. And it's really hard. Very few things survive that length of time unless you look at it very carefully. And we didn't have the equipment on board to do that. So it's since wandering up from the valley floor, it's been working its way up the hill mountain. This fantastic mountain is, high as Denali, in Alaska. It's just an amazing place, and it's a layer cake of history of Mars, and it's been just a wonderful way for us to explore and basically do stratigraphic understanding of the history of Mars, like studying the Grand Canyon, the layers of the Grand Canyon, exactly like that. Anyway, that's one side of Mars. And a few years later, some years later, quite a few years later, we landed Perseverance rover, and its job was to do something that our rovers cannot do, and that is to provide samples, collect samples, pristine samples that have virtually not zero, but nearly zero contamination from Earth in the sample tubes. And they're all sealed up in individual tubes, tubes about this big. You can see this video.
Oh, look at that.
Yeah, there's a sample tube. I'll put it right here by the, it's actually a wonderful writing instrument. But it's a sample tube. Samples just kind of live in here, and they're sealed up. There's this little glove that holds on to them. This is basically the tube, but we've been leaving this. We call it the glove because the vehicle, in order not to contaminate this tube when it's open, we hold on. The robotics hold on to the glove, and this is the glove that the rover has. And there's a glove for each sample tube, and we've been collecting them and dropping off. So Perseverance has dropped off 10 sample tubes in the Three Forks area of Mars in Jezero Crater. And in the meantime, it's dropped those contingency samples off. And the reason we drop them off on the ground is in the event that we have something happen to the rover, and because the samples that it collects now are in the belly of the rover, and they're relatively hard to extract for some other robot to come along and pull them out. But it's now, the rover is now up on the hill collecting samples. We're heading along the western rim of Jezero Crater, which has incredible geologic diversity. And we're very excited. The scientists are extraordinarily excited about the samples they've been collecting so far. And as they're collecting the samples, they're actually doing science on the samples to understand what the samples are mostly made out of, so to help select the best ones. And they've been doing that all along the way. And they're planning to do that for several years going forward here, collecting and filling out the rest of the empty sample tubes, and then eventually march back down toward Jezero Crater, hopefully in time to rendezvous with a future Mars mission that would have a rocket on it that would bring those samples back to Earth, called Mars Sample Return. And that's the challenge we have now is how do we fund and develop an affordable Mars Sample Return mission that we can squeak into the budget and make happen. And that's where we've been at now. That's really the priority. There's still plenty of other scientific questions. Many scientists would still like to have more rovers like we had with the little Spirit and Opportunity rovers that we sent in 2004, landed in 2004, that lasted for many years, longer than we expected. But those are actually lower priority right now for NASA. And they're kind of second order questions. The bulk of the scientific community really feels that we do not have the ability to send large, complex laboratories to Mars to do the kind of in situ, the sample analysis that you need to do to really ask key questions. And so the scientific community has, even today with better technologies, and even in the near future, we just don't have the technology to be able to do what we think we can do on Earth. So the scientific community believes very strongly the samples should come back to planet Earth, and that the scientists can, over the course of decades, do this kind of deliberative, focused, repeatable scientific experiments on those samples to be able to do to look for things like not just life, look for the signs of ancient life, residual life, not as living life. We don't believe
right.
We believe the surface is very sterile, but the organic residue of life that might still be there in some of the samples, and also other things like just understanding the times, uncovering the dating, the sequence of times. And you can do radiometric dating. You can do many other kinds of experiments on Earth it's really hard to do on a mobile laboratory on Mars. So that's the next challenge, and that's where we're at right now. And we've been working on sample return now. Again, sample return's an old concept, and we've been working on it now since the late 60s and early 70s. And in terms of iterating on the ideas and concepts and development, and there's been a lot of progress, huge amounts of progress of sample return over the years.
Well, let's talk more about that, and we'll do that as soon as we come back from the short break. Stay with us.
Well, since you brought it up, Rob, about Mars sample return, that's one of the big questions that I had. As someone that's been following the work that you and other scientists have been doing with these missions over time, I kind of feel like we were a little bit spoiled in the beginning, because we were seeing missions to Mars popping off every couple of years for a good long stretch. Each time that there was like one of those windows for the faster transits to get there. And now, since Perseverance, we really don't see like too much more beyond Mars sample return. But like you just said, there have been like thoughts and discussions about why we need to do this, how we could do it since the 60s. And we kind of find ourselves recently, hearing that NASA has to kind of go back to the drawing board because it's too expensive, $11 billion, whatnot. And I'm wondering what the biggest challenge, really is, why we're kind of not ready yet to really pull this off, when it's been a bit of a dream of scientists for quite some time. And it seems like the fact that we can put nuclear powered cars on the surface of Mars, like Perseverance and Curiosity, that it would just be maybe like a short step up, but it sounds like it's more technical than that. Is that I'm just trying to ask for people who maybe, don't really get how technical it actually is to do.
Well, I will, Tarek, the great question. I personally, I've been deeply involved in this for many years. In fact, I did my own math on this. That the sample return has been on average 9 years away from launch since the 1960s. And a lot of this has to do with, there's no doubt. So check this. So going back to history. So what's with this Mars drumbeat? Why was it so? Why were there so many missions that popped along? At least people's mind, there's so many of them. Actually, not that many, but there's still enough, handful or so. The reason is, first of all, Mars is close. You don't have to send something like Clipper to Jupiter takes years and has to swing by Mars, has to go around the sun, get enough energy, enough spin. It takes forever to get out there. It takes a lot of money, and they're very expensive. And of course, the environment at Jupiter is terrible for anything because of the radiation environment. Mars is really nice and convenient. It's still 20. You only have 26 months between launch windows, which is or launch periods, which is really, really irritating. I mean, you can't go whenever you want to, but still, that's pretty frequent relative to other planets. So we've been able to, and because there was so much about Mars we didn't know, we didn't have to really equip these missions like Spirit. Good example of Spirit and Opportunity, or even Pathfinder, Mars Pathfinder and Sojourner rover. We didn't have to put a lot of stuff on there to actually be able to answer some, to be able to get science back and new science. And so, but what's happened is we've basically plucked the low hanging fruit. We know how to do those simple things. And all these vehicles, of course, one-way trips. They land, they send their data back. We've learned a ton, and they've gotten more and more complex. Curiosity was a huge step in complexity and cost over Spirit and Opportunity. Spirit and Opportunity were about $870 million. I've got to adjust for inflation, so I can't quite do the math perfectly. It's not apples and apples, but whereas oops, I put my two thumbs up here. Look at that. Yes, I have a Mac. That
was an exciting moment. Yeah,
that was an exciting moment. I should do that again. Where's the cost for Curiosity? Because it's so much bigger over. We had to come up with a new landing architecture. The sky crane architecture, the sky crane maneuver to lower this rover like a helicopter on the surface of Mars, and then. So we had to do inventing all this stuff, and it took us longer, and we didn't make it in time. We had to delay our launch by 2 years, in order to get the thing finished in time. I was chief engineer for Curiosity, and I have to say it was a really hard road, and the cost was several times more than the cost of the combined Spirit and Opportunity budget, and so it's tougher. It gets hard, and the reason for that is because we were putting as much science inside Curiosity in terms of just mass, as though almost the entire weight of Opportunity rover. So put that in perspective. And by the way, the science equipment on Spirit and Opportunity rovers weighed about as much as all of Sojourner. So there seems to, if you see a trend here. The next mission needs the vehicle science payload, the mass of an entire. So that's what's happened here. So so the trouble with sample return is we have to, in order to carry so much stuff to Mars, the vehicles have to get bigger, they get more complex. In order to land something as heavy as sample return, as we've envisioned sample return with rather heavy Mars ascent vehicle, 470 kilograms, which is just the rocket. Compared to the mass of just the rocket that rides on top is a little payload. It's a payload element, and that's not the only payload the thing has to carry. The Mars sample return has to carry. Compare that with a 170 kilogram rover like Spirit and Opportunity. I mean, it's 3 times as much, right? It's incredible. I mean, and so it's not just the mass; it's the volume. Now the vehicle has to be bigger, and because the mass is so much higher, we have to invent all this new tricks and new sensors in order to fly this thing to the surface of Mars without crashing. So you have to layer all these new inventions on top of each other. I don't personally, the $11 billion. If you look at it, if you peel that onion and you go like, where'd you get that number? Because we never proposed $11 billion.
Okay, so let's hold on that thought for a second. That was my next question.
Okay, please do, Rod.
And we'll get to that right after this next break. Hold on. So as a layperson, and I admit a bit of a JPL fanboy, I have to say that, I see this tension, and I'm not sure I'm seeing it properly, but it feels like there's a tension between all this great engineering that results in missions that go on sometimes for well over a decade, when they're originally scheduled for a few months, which builds expectations in the public and in Congress and in the executive branch. And then this big challenge, which is many multiples of what you've done before, Mars sample return, the 8,000-pound gorilla, I guess, in this case. As we've said, we've talked about it for years and years, but the more you stare at it, the harder it seems to get, right? Mars just keeps getting more and more greedy in terms of, I don't give you enough atmosphere, but I've still got enough gravity to make it the pain in the neck and all that. So, I mean, is that a tension there, or is it just the raw cost that they're reacting to?
There is that tension. I mean, sample return has one feature that other Mars missions don't have. And that was even with Perseverance, which is sort of slowly collecting samples, you really can't call it mission success. It's considered, by the way, mission success already because it's past its mission life already. But most missions, you land and you start collecting science and you send the science back by your radio, and the scientists start going, yay, we're getting more information, we're getting more, and they're getting more and more and more of the time. Sample return has this really irritating property that you get no joy, zero joy, until the samples have landed on Earth and have been stored and opened up inside a sample receiving facility. Years and years later. So it's like it's the worst delayed gratification of any Mars mission you can imagine. Right. It's like you've got to have incredible patience. And meanwhile, you're forking out tons of money over years, right, to pay for all that stuff. And so there's a sense of investment that goes with sample return that is unlike any other Mars mission. So that's sort of an emotional and kind of a quasi-political anxiety that goes with this. So you have to be super committed and super patient. And in our society, that's not one of our major attributes. Patience. I mean, to say, hey, we're going to get this in the laboratory in 2032, 2033, that'd be great. It's like, oh my God, am I going to be live then? So a lot of people it's understandable. And if you're a scientist, you have to be willing to put out a lot and be willing to take the long game.
And I wanted to follow up on that because I was trying to look at like the cost of one versus the cost of the. You mentioned the kind of labels in terms of price tags that have been put on Mars sample return itself, but like Perseverance, I think, is estimated at $2.7 billion, and you get a lot for that, right? You've got these samples that are cached now. You've got a long-lived rover that's doing all sorts of things. It's climbing a mountain on Mars, and then the next evolution for a much larger vehicle. The cost that NASA has been talking about and saying is too expensive is that 11 billion number, which it sounds like you have some stuff, some thoughts to kind of really put that in perspective. Well, but I did want to say my father-in-law has a saying, that if you pay peanuts, you get monkeys, which is, basically you get what you pay for. So if you're not, like, to your point, willing to commit in advance, and we discussed this at length about several other subjects, Rod and I, if you're not going to commit to spending the money for what you need to do the work, then no one's going to be happy. But it sounds like this number, this 11 billion might not be, the sticking point that it sounds like. I mean, if you could, because it sounds like you've got some stuff to talk to us about that.
No, I think you're right. I mean, to be fair, if you look at the $11 billion where it came from, it's actually they said, okay, well, what's the worst it could be?
Yeah.
And particularly if you live, given all the constraints, NASA, for example, is to listen, hey, we don't have the budget we used to have. We've got other priorities, Artemis, we've got other things to do. This is not number one in NASA's priority list, you guys. This is, it's great science. We love science, we're fans, but we've got other science too, and there are other scientists who are chomping at the bit. We want to go to Venus. We got other things we need to do. We have more astronomy stuff to do. It's getting, we can only allocate this much per year, and so they said, okay, if you did that, then you would have this. In order to develop this stuff, you would have this small standing army that would do a little bit at a time. It's kind of like if you did build your house, but you can only afford a couple $1,000s a year to your house, and then you start collecting wood from Home Depot. You start putting stuff in the corner. You still have a few employees because you have to keep designing it to make sure it works, and you start putting the pieces gradually, and you integrate that over long periods of time. It turns out, and you add inflation on top of that. Yeah, pretty soon you're talking about some real money.
Well, and if you leave your wood out too long, it starts to rot before you have a chance to put up the roof.
Well, I won't even go into those kind of details either, because there's human factors issues too, like corporate knowledge and memory. And how do you retain that? So that's what they did. So this is what the worst case, and that was considered. That's not acceptable. Well, yeah. By the way, samples get back in 2040. And that's like, no one has that kind of patience apparently. It's a long time from now, right? 2040, is that a long time? Well, and I bet you if we had a time machine, I asked you in 2040, was that a long time ago? You go, no, it wasn't that long. Actually, it didn't take that long to go from 2024 to 2040, but in our world, it is a long time. It's hard to commit anything for that period of time. So it's a lot of challenge. I mean, so the reason, in some sense, there are ways of making the thing a lot cheaper and a lot easier to do, but it requires something that NASA can't do right now because of the constant constraints, and that is putting a big pile of money on it over a small number of years. And because you can fund it this way, or you could fund it and get it over with. And so many of our missions, and that's the cool thing about Mars with the 2-year lifetime. There's this wonderful drumbeat of we can't be late. We got to get the money in there. We got to make it happen. Because if you missed your launch window, your 2-week launch period, you'd have to wait 26 months before you can go again. And that's going to be ka-ching because all these people have to kind of hang out and wait for operations, and you just can't lay them all off and then hire them back again because they're not going to be around. They're going to be working for Blue or SpaceX or whatever, So you're stuck.
And we've seen examples of that with the European Space Agency's challenges with ExoMars. I mean, they had delays, they missed a window, then they came up with the next window, then there's a war in Ukraine and they lose their launch vehicle.
I know.
And then now they have to wait again another 2 years. And so there's other forces beyond
tragic.
Just the technical ones too that could happen.
I feel so bad. Yeah, I feel so bad for those guys. They work so hard for so long. And they're great people there, but it feels Kafka-esque. The kind of their scientific that effort where something seems to happen and you just never couldn't get there. It's very frustrating. And I'll be honest, we have been incredibly lucky to have had a consistent funding, consistent drumbeat, biting off things that were not too expensive, that were affordable, that people could actually commit to. But if that commitment level raises above a certain threshold, it's like, no, we can't buy. That's just too much to swallow for a particular launch window. And I think that's the situation we're finding with them, Smart Sample Return. It's just like, today we look back at James Webb and we go, wow, $10 billion worth every penny. We're getting some amazing things. We look
because it opened. Yeah.
It all opened, it all pulled together. And, the science we're getting is, revolutionary. And it really is. And I'm so amazed and thrilled. But, if you had said, hey, can I get $10 billion from you guys? And then go like, you got to be kidding me. No. That would eat the rest of science and astronomy missions lunch for the next decade. And that's all we'll be able to do. And they go, well, maybe that's the only thing we can do. And that's what we did. But ultimately, that's what happened. They actually did do it, and they kept up, and they didn't give up. NASA, ironically, I don't know if you know that the sample return program, we never got to the point of actually submitting a budget for it. So everybody's sense is, guys are too expensive. Well, we actually haven't told you how expensive it is yet. We haven't had our PDR yet.
Because we have this number thrown in our face over and over again. First it was 7.5 billion. Now it's 11 billion. And the only way I can think of to get Congress to just say yes is to tell them North Korea is about to return robotic samples from Mars. But where's that number coming from if it's not from you? Because they keep pointing it back to you.
Well,
to JPL, I mean.
I'm not going to answer that. I have no idea. And I mean, I think they would like us to be cheaper. Everybody wants, but we know how much things cost. You've seen how much stuff, how tough it is to make Curiosity and Perseverance and Spirit Opportunity and Pathfinder and Mars Reconnaissance Orbiter, all these different stuff we've been involved in. So, it's just, listen, what they're trying to do, and they're doing the right thing. They're saying, hey, you guys, we don't know yet how much it's going to cost. First of all, we haven't finished doing the math to do the estimate. So we have not submitted an official estimate, because the NASA has something called key decision point, KDPC, where you commit to a life cycle cost. We haven't got there yet. We never got there. And, but there's no doubt that the way it was set up, it was going to be expensive. And no matter what number, whether it's 11, 7, 6, doesn't matter. It's a big number. Just say big. Don't say number. It's going to be big. Can NASA afford big? And the answer is, I don't think NASA can afford big right now, because we've got higher priorities than that. And it's really, so the people who are saying it, they can point to wherever they want, but there is no doubt it's hard. I mean, I'm on the review board for these things and these projects, and it's daunting. The size of that lander is really big. I was the chair for the Inter-Descent Landing Review. They're pulling out all the stops. For example, when this vehicle enters, in order not to hit the surface, this ballistic entry, they dive as deep as they dare into the atmosphere, quite steep. They fly horizontally, and then they pull the very large center of mass offset, is the largest ever, to pull up and try to get more lift and get it higher above the ground. And so it actually does a scoop, a dive and a pull up, where we can be high enough to open the parachute and have enough timeline to get to the surface. And while they're doing that, the vehicle doesn't know where it is and needs to help guidance. And especially if it's lofting in the air like this, it needs to look out the window. So now, for the first time, normally we look out the window once the heat shield is gone. Now we have to add a window, look out the window while you're still flying horizontally toward the ground to see where the heck you are, so you can help control and guide your entry better. Again, all trying to squeeze this incredible mass into this fixed volume, and so it's a challenge. It's a strong, difficult engineering challenge, and not to mention we have to put a next step up in parachute size. And all that stuff is because we're trying to land this massive rocket, and with a European arm in it that does the sample motion and handling, all the other equipment we need to be able to control the temperature of this system, and have all the features you need to do. The sample container, the OS, we call it, the orbiting sample container, has to have has to be a double sealed in order to prevent back contamination with Earth. There's a whole bunch of things, and the orbiter has to carry all this stuff with it. I mean, it's even that the Europeans have been struggling with this growing mass of this equipment we needed to bring with us in order to capture and seal up and store and return the samples back to a direct return back to Earth. And all this stuff is because we're trying to find ways to capitalize on the partnerships and the relationships, and it turns out it's actually probably more expensive to do it that way. There are ways to do it cheaper, but you have to be willing to take risks. You have to do
well, and that's an interesting separate topic. Is this isn't, again, as an outsider, my impression has always been, if you're working on NASA missions, which are of course funded by the public and overseen by the executive branch, which likes to affix a certain amount of status to success, failure really is not an option. Whereas if you're SpaceX, you can fail all you want as long as it's not being paid for by government. But before we get back into that, let's take one more break, and then we'll be able to to ask Tarek's next question, which I could tell he's bursting at the seams there.
Rob, it sounds exciting what a Mars sample return mission would be like, but it also sounds like it's super complicated, which we've been talking about this whole time.
Yeah.
And I know that there's been like a few hundred, actual Mars samples that we've discovered on Earth with meteorites and whatnot.
Right.
And I'm just wondering what story they're not telling us. That pristine samples.
That sounds a little paranoid to me, buddy.
Because it's a general question about what those pristine samples, either of Martian regolith or the rocks themselves, and I guess these special samples that Perseverance, collected, because there's a difference, right? Perseverance has some what is it? Not genealogy, some provenance to their samples, whereas just landing, grabbing a scoop of dirt, shoving it in a rocket and bringing it back is a little bit, different than the kind of approach that we're looking at right now. So what do you glean from the pristine part that we don't get from these?
Okay, so it's actually pristine is one of the pieces. You asked a good question. I say what don't our so-called SNCC meteorites discovered on Earth? The Mars samples, Mars meteorites, rocks that have come from very high confidence, we know came from Mars because they contain the trapped gases match the isotopic ratios you see on Mars samples that we've measured on Mars. So what don't they? How come we can't get the information? We get a lot from them. There's no doubt about it. But there's a lot of things. A lot of things we love to ask this rock about its history that it's not willing to tell us. One of the problems is these rocks have, in order to get to Earth, they were shocked and sent into space. So they were altered by the actual impact, which launched them out from Mars.
An impact by like something hit Mars. And
something whacked into Mars and spit them up, and they got affected there. So whatever history they had, some of it is wiped out, some of it isn't. And then they spend millions of years in orbit around the sun, many millions of years before they get a chance to bump into our little planet. Okay. And so they get altered. They get altered by cosmic rays. They're exposed to the environments and the temperatures in orbit around the sun. They're like little planets of their own, right? Asteroids. And eventually bump into Earth. And of course, they go through the entry phase, which is not that's most of us, if you were a rock, you would melt a little bit, and so you get affected, and then you end up spending thousands, maybe not, in some cases, hundreds of thousands of years on the surface of the Earth, getting rained on, snowed on. And so your story is there, but it's stomped on by the rather tough history to get here. So there's certain things, and so much of what you lose, you have to ask the question, is that rock? And this was true for the infamous ALH 84001 asteroid, a meteor that landed and was found in Allen Hills area of Antarctica in 1984. And they thought was, they tell a really interesting story. The question is there's another thing that was missing about that, because there's many parts of it go like this was not affected by that journey. Mm-hmm. Like those
this is little wormy looking things we found that turned out to be geological in nature, right?
Exactly.
Yeah.
Well, it turned out to have a possible geologic origin story. In other words, we don't know, right. But we can't say for sure it was biological. As Carl Sagan's to say, extraordinary claims require extraordinary evidence, and this evidence had at least two possible explanations. And so the problem was that context is everything. So what the cool thing that Perseverance is doing, when it collects a rock, it knows the context in which it is being collected. It knows its geological region it was collected in. We know something about its overall temporal structure, whether it was a rock that had been laid down billions of years ago or had been altered by recent millions of years ago kind of events. And you can get that context. And so by putting that story together, they'll be able to layer all the other observables they have into the storyline that goes associated with these samples. And you can discount all the impact, the effect of the journey will be minuscule compared to the impact of a journey going from the surface of Mars to the surface of Antarctica. So that is the story, and that's what that's the architecture, and that's the reason. By the way, so you might ask us, well, Rob, why don't we just we get content? Why don't we just go out and grab a scoop, put it in? That's called a grab sample, and that's been one of the many architectural elements of sample return for many years, decades. Over time, the story I just gave you about why the context is so important. The trouble with grabbing a pile of regolith has the same problem, similar problem, is that it's a pile of dirt and you don't know which rock it came from, where it landed from. You end up losing the historical context of that sample. So that's why we core into rock, because rock has not been decimated. It's actually typically formed in that rock. Those were those minerals were formed. And so the idea of grab sample is fine. You learn something. It's not definitely it wouldn't be but here we have these little samples, and we're able to pull them together in this incredible diversity, and we'll be able to lay them on the surface of Mars or deliver them directly to a lander. Whether it's a pile of rocks in a pile or a bunch of these sample tubes, really doesn't matter. The sample return is still hard because you need to put them into something the size of a soccer ball. Okay, the soccer ball has the samples in them. I don't care how you organize, how you what you do. You need about a ball about this big, and it's a handful or so of kilograms. And that you need to get that in outer space. Okay.
Right.
That's all you need to do. How tough can that be? Come on, guys. You can just do it. Throw it up there. Put it in a cannon. Do something.
If you can drive to many more places.
He said a cannon.
You can drive to places that are more interesting than where you can land, right? I mean, the engineers are always going to, maybe not you, but the room of engineers when you're debating landing sites is going to say, okay, put us on that nice flat basaltic plain with a little bit of gravel on it. And then the geologists are saying, I want to be close to that river delta. And but my real question is, and then I'm going to give Tarek his, that's probably all I'll have time for. There's this, and maybe I'm thinking it and you guys don't need to, but it seems like there's this tension, because you're looking at this long timeline for MSR, Mars Sample Return, maybe there's this tension potentially between, it's going to take us, say 12 to 14 years to get a sample back from Mars, but we might be able to get human beings there in 18 to 20 years. Is it urgent to get those samples back before we send a human crew? Or do we think that the human landing there is really going to be, out in 2050 and let's just move on with samples?
I think depending on who you talk to, I think I don't think there's a story. First of all, I'm not an expert here, so I'm going to defer. My personal understanding is that there are things that you would learn about crew safety from a sample. Mm-hmm. If you are a planetary protection expert, you would say, hey, I really need to assess the biological potential of those samples for protection, for possible back contamination into humans and back in our planet. Presumably, if an astronaut goes to Mars, they have some hope of coming back. And if they're contaminated, that would be bad. Mm-hmm. So they would many people would like to be able to say, certify that Mars is indeed a safe place to go in the samples, and whatever residual samples, including the contamination to the astronauts themselves, are fine. The other thing, a lot of people think, if you look at the total because we have all these very intense forward contamination requirements, we are very, very careful to minimize the amount of biomass that we actually deliver to Mars.
Right.
We have this appears to be a large number, 3 times 10 to the 5 spores per mission. It sounds like a lot, 300,000 spores. But if you put that on the head of a pin, you still wouldn't see it. It doesn't weigh anything. A crew of people, I tell you, are dirty. It's just the way we are. It's like part of us, and it's going to be very hard for us not to contaminate significantly contaminate the area of Mars that they land, and provide and actually, submit biological material to the surface of Mars from Earth. So the first human crews are going to be actually contaminating Mars, not the whole planet, but portions, at least where they're at. Some of it will actually migrate through windstorms and dust storms and kind of fly around, but it's not going to ruin our ability to actually sample pristine samples of Mars.
Right.
However, it's going to start the clock's ticking. We're starting to do it. I mean, everything we crashed into Mars or landed, everything, we worked really hard to be super clean, including the Europeans. Everybody does it that way. We follow norms that are established through the United Nations. And so but crew's going to change all that overnight. So there's a bunch of arguments like that. So, and there are things about the samples. We'd like to know more about the potential for how the Mars particulates could, if we ingested into lungs, what happens to it. Of course, we wouldn't actually test it. Rod might be available, but I think, ouch. No, so listen, our early days when we thought of samples, we thought almost fully half the samples we've been bringing back would be ingested by biological creatures on Earth as part of our test program to validate that the sample. We've since learned we don't have to do that because we have equipment that on Earth that could actually say, no, we can just look at them, with a microscope. But still, so there's some of that. The question is there an imperative? Maybe. I mean, it's a risk thing. And the question is a lot. So we one of the reasons sample return is so expensive is we have an extra requirement that most missions don't have. We have to make sure that we have a very low probability of inadvertently releasing samples into the Earth environment.
Right. So we don't get space plague, right?
Right. Yeah. It's the Andromeda Strain concern, right? The movie, Andromeda Strain. Do you remember that? No, most people think it's extraordinarily low. I mean, the pathogenic it takes a lot of work for pathogens to evolve in the first place. They tend to evolve as part of a competitive environment, competitive in the sense of a genetic competition in a Darwinian sense. So it's unlikely that they would, but we don't know for sure. That's the thing. The probability is not zero. And so we do this enormous amount of work of sealing, we call breaking the chain of contact. So everything that's delivered to Earth is clean, guaranteed to be clean of Mars stuff, and anything that's inside it's Mars is protected and sealed up from the outside. Mm-hmm. So we put a lot of effort into doing that, and a lot of that equipment is what's burdening the mass of the orbiter and burdening the mass of our samples that go up from our rocket. This is the kinds of thing, and this takes a huge amount of effort to figure out how to get this right. And so we do this special sealing techniques and special. Our plan was to surround the OS with this massive array of very bright ultraviolet sterilizing light. This would be the brightest thing the biggest light bulbs ever sent to Mars that's surrounding our view. This is the kind of thing that we had to do in order to convince ourselves that these are the kinds of requirements that cause things to be expensive.
Yeah.
And so anyway.
I had one last question that you've got me thinking of, and it's just about the future, because we've been talking a lot about Mars sample return and the history of these Mars missions and how they got bigger, more complex, and whatnot. But I'm wondering what's beyond Mars sample return. Is it something like we're seeing at the moon, where we're getting smaller but more targeted, like rovers to this spot to drill for ice, or that spot, or this orbiter to be a communications thing? What would the next few windows be that you would want to target if you could pick the missions?
I'm an engineer, so I can't speak for the scientific community, but the scientific community that I've heard so far Mars is so rich and diverse, so many cool things to look at. They will give you a list pages long of things they'd like to see. They understand that we need to neck down to the single priority. And so a lot of them are just like, okay, well, all the things I want to look at, we're not going to be looking at it, until I'm an old person. But so they're all kind of agreeing the sample return is the number one priority, and that's budget is big enough so it would gobble up all the other budgets to do that kind of thing. So the question is are there other things? And by the way, and certainly NASA's view is, well, and maybe SpaceX and Blue Origin's view is that Mars exploration is next, and there's going to be a human doing this, and all these questions that you want to answer you don't need a Sojourner or Spirit Opportunity rover. We'll just have astronauts do it. Thank you. But something that's really, something we all need to be aware of about why Mars is more difficult than the average bear. When we're all, because we're all engineering space groupies, right? We like I love watching the videos of what the progress of Starship, and the wonderful engineering trial and error iterative approach that they're able to use on a very fast turnover. It gives me chills. I mean, I so wish that we could do that. The problem is, how do we do trials if each trial is separated by 26 months?
Yeah.
And so it's very painful. So you have to do all those trials here on this planet somehow, and faking out the tests that we do or development to make it kind of Mars-like-ish, and it's really hard to do because Mars and Earth are nothing close to the same in so many different ways. And so it's hard to find that, and that's one of the reasons our missions tend to be more expensive, because we're doing things, when you see us cheering with our blue suits and going and crying, all that stuff, that's not happiness. That's relief that we didn't mess up. We've gone through thousands and thousands of possible things in our mind's eye with tests and checking out. We have to get it right the first time on national television, with everybody watching us. Can you imagine that kind of pressure? It's
actually
out there.
Yes.
Yes, you can.
So it's just a quick lightning round answer on this one, if you can. Depending on what happens with Mars sample return, go either way. But in terms of sitting at JPL and looking towards Washington, is there stuff coming down the pipeline, or are we entering kind of a quiet period here?
It appears to be very quiet. We're it's very. I will admit we've had layoffs at JPL. It's been very. It's been challenging, very challenging. Our staff are concerned, and my concern is not. I mean, the cool thing about the kind of work that we do, almost everybody has no trouble finding a job outside if they want to go. I mean, there's plenty of other places that'll pay them to do this kind of work. We are a bit of a renaissance. I hope it lasts for a little longer in the space business with the new space, and there's a whole bunch of great inventors. There's no shortage of creativity out there, and we've got people who are exceptionally creative and capable people, and who will find things to do. I'm more concerned about just our memory of how to do this kind of stuff. It's so
because you experienced that firsthand with Pathfinder, right? You wanted to go back to Viking lander technology, and it was gone.
Gone. Yes, exactly right. People wonder why we did this silly airbag and solid rocket bouncing thing on Mars. It's because we couldn't afford the cost to reinvent and redevelop throttled engines that would allow us to land like Buck Rogers is supposed to do. And so we end up with this goofy Rube Goldberg and very low cost, mind you, very cheap landing system that worked very well. And we copied that same design in most of Pathfinder, and we just put wheels on Pathfinder, and we call them Spirit and Opportunity rovers, right? So we use that to keep the cost down and complexity. But to do Curiosity, we had to reinvent and fund over a long period of time throughout the early 2000s before we launched Curiosity, those throttle engines technology that had to be reinvented, and that budget just to do that was a significant fraction of all of Mars Pathfinder's budget.
Right.
And so,
and this could happen again and again.
Yeah, and so the kind of thing is easy for people think that we advance in steps and we go backwards. We don't go forwards all the time. And by the way, who's the we? A private company that can invent something and do something magical. If that company runs out of money or goes bankrupt, all that knowledge goes poof,
right,
disappears.
Well, and that's a good argument for keeping things moving. But speaking of keeping things moving, I have to wrap up, and I'd love to have you back. I personally, I'd love to do a whole episode on EDL because it's such a fascinating story. But for now, I want to thank you for coming on today. I want to thank everybody for listening to episode 112, This Week in Space, The Great Mars Pause. And don't forget to check us out on space.com. The website's in the name, and the National Space Society, of course, at nss.org. And if you happen to be in LA and you're looking for something to do this weekend, our conference is running at the Sheraton Gateway down by LAX, and we got all kinds of cool stuff happening. Unfortunately, the coolest thing was Rob on Thursday, so you missed that. But there's astronauts and other NASA luminaries and so forth. Even William Shatner is going to be rolling by. So if you get a chance to come down, please come say hi. Rob, where can we best track down your adventures in the future?
Well, just call me. You know where I live, Rod.
I meant everybody else.
Oh, everybody. I don't actually do social media, so I don't do a very good job of sharing my stories. I have to kind of teach myself how to do that. But I might do that more now that I'm no longer representing JPL as a whole as chief engineer. I might be able to do more of that and share my thoughts and ideas more as an opinion person as opposed to a representative of a big institution. So
excellent. And Tarek, where can we find you wasting your life on video games?
Wasting. That's the wave of the future, Rod. But no, you can find me at space.com. As always, this weekend we'll be, not just celebrating Memorial Day as the holiday as we're recording this, but also watching Rocket Lab launch NASA's pre-fire mission to study the Earth, and like never before. So that'll be really exciting. It's the first of a couple of satellites for that mission. And as Rod alluded to, there's a new season of Fortnite, the Wrecked season, with Fallout and everything is in it. There's not a lot of space, so I'm a little disappointed, but I'll probably be doing some of that this weekend.
Well, and because I'm apparently backward looking and curmudgeonly, you can find me at pilebooks.com or at astromagazine.com, where we publish our quarterly magazine for the NSS. Please remember, you can always drop us a line at twis@twit.tv. That's TWIS@twit.tv. We welcome all your comments, and especially your jokes. They don't even have to be good ones. Actually, if you send us some of your worst, that can be for a good afternoon. But we love your comments, and we do answer every email. New episodes of this podcast actually publish every Friday on your favorite podcatcher, so make sure to subscribe, tell your friends, and give us reviews. And don't forget, you can get all the great programming with video streams and all the extras that you don't see behind the firewall on Club Twit. Only $7 a month. It's a heck of a deal, and we'd appreciate it because podcasts are struggling, and we don't want to struggle. We want to spend our time talking to cool people like Rob. You can follow the Twit Tech Podcast Network at Twit on Twitter and on Facebook and twit.tv on Instagram. Thank you very much, and we'll see you all next week.